Political power grows out of the barrel of a gun. To every action, there is always opposed an equal reaction. Victorious warriors win first and then go to war, while defeated warriors go to war first and then seek to win.
Uniquely how charges will move, what acceleration they will obtain. That means how their kinetic energy will change. And the answer is yeah. If you know the electric field everywhere in space, sure, then you can predict everything that happens with a charge in that field. But there are examples where the electric fields are so incredibly complicated that it is easier to work with equi-potentials. Because the change in kinetic energy, as I will discuss now, really depends only on the change in the potential when you go from one point to another. So you will see very shortly that sometimes if you're only interested in change of kinetic energy and not necessarily interested in the details of the trajectory, then equi-potentials come in very handy. Never confuse U, which is electrostatic potential energy, with V, which is electric potential. This has unit joules, and this has unit joules per coulomb, which we call volts. If I have a collection of charges, pluses and minuses, U has only one value. It is the work that I have to do to put all these crazy charges exactly where they are. But the electric potential is different here, from there to there, to there, to there. If you're very close to a plus charge, you can be sure that the potential is positive. If you're very close to a negative charge, you can be sure that the potential is negative. But U has only one number. It's only one value. They're both scalars. Don't confuse one with the other. In a gravitational field, matter, like a piece of chalk, wants to go from high potential to low potential. If I just release it with zero speed, there it goes. High potential to low potential. In analogy, positive charges will also go from a high electric potential to a low electric potential. And of course, this is unique for electricity. Negative charges will go from a low potential to a high electric potential.
Captured lots of operations, and surprisingly there were many operations going on in these circuits that could be seen with quaternion electrodynamics, could not be seen with the best tensor analysis you could do this work. And most of the conventionally trained scientists assume that they know and understand everything Tesla did. They do not. One of the really fine electrodynamicists and electrophysicists we have in this country is a man named Terry Barrett. Barrett took a look at Tesla's actual patents, but he looked at them in quaternion algebra, the same kind of thing that Maxwell was originally using in his original theory. And surprisingly, there were many operations going on in these circuits that could be seen with quaternion electrodynamics, could not be seen with the best tensor analysis you could do. So Barrett published a paper on it, to show what was actually going on in those circuits. He also saw some ways to improve what Tesla had been doing, and he filed and obtained 2 patents which are still used in communication industry and things like ultra-wideband radar. So it does work. But my point is that we started off with this better model, but it was much more complicated mathematics. Now in those days, the fashion was to call what we today would call electrical engineer, call them electricians. And most of them were more like electricians than what we would consider an electrical engineer. And for example, people like Heaviside looking at that said, you know, these poor electricians, they'll never learn these silly quaternions. That's far too complicated. This has got to be made simpler. He wasn't the only one that took that view, but he was the major one that played a major role in cutting down those equations and making them much easier and much simpler, and therefore losing lots of operations you can do. But a quaternion has one peculiar thing. It takes a vector, what we today will call a vector component, one that has direction as well as magnitude, and it sticks on the component that doesn't have any direction, just has magnitude. And people like Heaviside, who was totally self-taught, never went to university at all, but brilliant man, brilliant. We're not knocking Heaviside at all. Heaviside said, that's mixing apples and oranges, so let's chop off that part that's not got a direction. And that's the way vectors were born. Heaviside and Hertz and primarily an American also named Gibbs.
Dust, one of nature's mightiest multipliers, takes the golden dust from a trickle to a roar.
No matter how many times I see it, just wow!
Indeed.
Sorry, yes, me again. Coming through. No, don't get up. Oh, sorry, I should have flown, right? What did I miss?
Snow! Wow. You did it! You actually did it! Whew, it's cold. done for the day? Rest up, because first thing tomorrow, we're gonna find someplace great for you. Just until things settle down. Gruff, you see those stars over there? If you connect them, they make a monkey. See his tail? But if you turn it upside down, it's a swan. See? That one's a squirrel. Oh, and over there with the spikes, hedgehog. See it? I knew you'd get it. You just have to know how to look. Here we go.
It worked! Yeah, she did it!
Magic people, voodoo people.